Hello everybody, this is David. Welcome back to the microprocessor series on the 7-step processor, and welcome to part 2, the arithmetic and logic unit. So as you remember, last video we talked about the processor. This is the complete processor. We're going to be focusing on the ALU. Last video we did the RAM over here, the main memory, and now we're just going to be focusing on the ALU. Notice the connections to it. We just have the 8-bit bus for A, we have an 8-bit bus for B, we have 3 bits for the opcode, 1 bit for a carry in coming in. These are inputs here, 4 bits as an output to the flags register, and the 8 bits result coming out going into the accumulator. We're going to go through each part that will be part of the ALU. So we'll start with the adder. So this is a half adder. It operates on 2 operands, right? Operand A and B. And the reason why it's a half adder is because it doesn't have the carry in. So when you add the carry in, then you get the full adder. So this is essentially what we have here. And for each set of bits of A and B, so if we have 8 bits for A and B, we'll have 8 sections of these that'll operate on each section. And then there's a little bit more to it, but that's the basics of it. And then this is the symbol for it down here. We also have left and right shifters in our ALU, and I turned the picture sideways so that they actually look like the bits are shifting left and right and not down and up. So you can see how in the left shift, which is on the left, we are shifting out the high order bit. So the result is here. It only operates in operand A. So in R1, oh dang it, I want to go back. There. Essentially in R1, we have operand A, and we're going to shift it left, and that'll shift out the higher order bit. And we can also use the carry in bit to shift in a bit into the low order bit. And the right shift works exactly the opposite way. Here's a notter, just like it says, and it only operates on 1 operand. It's just going to take the not of each signal. The ander operates on 2 operands. It'll and each one together. The bitwise and, right? Same thing, bitwise OR right here on 2 operands. Bitwise exclusive OR. And then we come to the final part of the ALU, the comparator. And it's essentially an exclusive OR, so you're going to get the same result of C as if you use the XOR operand. But in this case, using the comparator, we want to set flags whether A and B are equal, so we can check if they're equal. So in a program, you know, if you ever looked at a software program, you might see like an if statement. If A is equal to B, then you perform some other kind of code. Well, this is exactly how you find out, is using a comparator, and it has a bit that will be set if they're equal, and we'll also have a flag for A larger than B, right? A greater than B. So you can jump in your code. And so here's our entire ALU all together here on the left. This is the entire schematic for it. Here's the symbol over here on the right that we are going to use to create our Verilog module from. And here is a breakdown of all the opcodes and what they do. And you can kind of see right here on the left how A and B come in, and each of these gets to each of these gates. There's also the carry in. Here's the opcode. Is essentially a decoder which decodes which AND gate to activate to right, or to enable right here. Yeah, which one to enable the you know, essentially like a multiplexer, right? You select which one you want to come out on C. So when you put A and B here at the ALU, whatever you select as the operand is what's going to come out on C, right? But all of these operations are still taking place. You're just selecting which operation you want to see come out. And then you also have the outputs for the flags. So now let's get into the Verilog code. Okay, welcome back. Here's the Verilog code right here for the ALU, and we'll go through the inputs first. We have the 8 bits of operand A, 8 bits of operand B. We have a carry in bit to make a full adder, right? 3 bits for the opcode, an 8-bit result for C, and then our 4 conditional flags. The carry out, A larger than B, A is equal to B, and the ALU result is 0. Now here's the some parameters, just naming all of the opcodes simply using octal notation, and giving them symbolic names so we can understand what we're supposed to get when we do stuff like this, right? We have the, you know, it'll make sense in the test bench as well, but essentially if we're, well, let me back up here to this register. Why did I add another bit here? Well, we need a 9th bit for the carry out from addition. So the output is essentially down here, right? It's 8 bits of this 9-bit register, but that 9th bit is what's going to carry. It's going to grab the carry out from addition, right? Or from a shift. Now, let's see. Okay, so we'll go through each opcode. Add, we're adding A plus B plus C in, right? Right shift, we are going to concatenate with a carry in, which we can set to either 0 or 1 to carry in from the right side, and then we're just going to shift over the bits. Same thing going back to the left, we're going to shift over the lowest bits to the left and then carry in to the left. The not, right, this is how you do it in Verilog, simply just tilde A, right? It only operates on operand A. Here's A and B, A or B, A XOR B, and then here's the comparator, but the difference is we're using this operation to set flags, and we will define that down here. So I already said the result is the outreg, the 8 bits, the actual ALU result. In order to check if the result is 0, we're going to do a reduction NOR on the result, and that will tell us if we have all bits are 0. Here's our equal, only when we're using the compare opcode, and we have and the 0 flag is equal to 1. Are they equal? Right, because if they're equal, you should get the 0, because an XOR, if you have two 8-bit value or two any bit values that are equal and you XOR them together, you'll get a value of 0, right? That's what XOR does. You have one or the other, but not both the same, whether it be same 0 or same 1. So then we'll set, that's how we set the equal flag. A larger in the compare opcode, and if A is greater than B, quite simply, we'll set that flag. And here's the carry out. If we have addition, then we want to grab that 9th bit of the outreg. If we're doing a right shift, then we are going to grab the low order bit of A that we're shifting out. And if we're doing a left shift, we're grabbing the higher order bit of A in the carry out. And that's the whole ALU module. Here's the test bench. Just created some signals, some registers to drive operand A and B and the carry in. Also the opcode. Everything else we're just going to use wires to capture the information that comes out. That being the result, and then the 4 flags here. I'm going to use the same parameters in here so I can just do that in the simulation. Here's instantiating the ALU and connecting all the test bench signals to the I/O of the device under test. Here's that same dump file and dump vars, just with a different name to follow along with what it is actually. Okay, now we get to the payoff. Now we're in the simulation and we're initializing the registers. I'll just initialize CN to 0 for now. So what I've got here for the simulation is, if you see the arrow coming in, that's when we're setting an operand for A or B, and then this is what the output should be. This is the expected output of for each operation, and we'll set values of A and B, and we'll go through and we'll do each operation. Here we start with the add, which if you add these two values together, you should get this value, right? And then if we add one more with a carry in, that should flip this all to 0, and we should get a 0 flag set and also the carry out set, because this bit here will have to get pushed out. The 1 will. And so we're going to check all the operations, right shift, left shift with different values, also using carry in, and we're also going to check if the carry out gets set. So we'll put 1s on both ends. So hex 8 1, a 1 on each end. We'll right shift, check the carry out, then we'll left shift and check the carry out. We'll do a not, an and, or, an XOR, and then we'll do a compare and check to make sure the equal flag is working. And we should also get the 0 flag at the same time if they are exclusive OR and they're equal. And then we'll come down and do the compare again, looking for A larger. So we'll change A to a little bit larger than what B is, and we'll check for the A larger flag. All right, I'm gonna run the simulation, open GTKWave. All right, if you don't remember from last video, or if you need a refresher about this, once again, here are the commands for Icarus Verilog. The Verilog-O, I just name it ALU because that's what we're testing. The two Verilog modules, VVP, ALU, when you get no errors, GTKWave, your VCD file. All right, once you run those commands from your command line, you'll get GTKWave pop up. Expand this up here to expose the device under test, and we will bring all the signals in except for, I don't want to look at the out reg. And we'll put these in the Wave viewer by appending or inserting them. We will expand it with this. I want to come open and add a little bit more room. I'm going to change all these to binary. So you'll see why it makes sense to look at it in binary here in a second. So, let me rearrange these signals a little bit. Okay, good to go. Now, at the first clock cycle, what did we do? We set operand A equal to hex AA and operand B equal to hex CC, and then opcode 000 is adding them, and we get all ones. We get hex FF. That is correct. And then once the next clock cycle, we're adding the carry in, which will push one bit out into the carry out, and it'll also make the result 0, and we get the 0 flag. So that works out good. Then we just take the carry out or the carry in off. We're back to all ones. Now here we want to right shift. This is right shift first, right? So look at operand A up here. It's 0C. So we have the 2 1s here. You can see how they get shifted over one place. All right, and now if we're adding the carry in on our shift, we can shift in we can not only shift the values to the right, but we'll shift in that carry in bit right here. That's just taking it back. Now we're left shifting. So we start with this value of A up here, and we are, you can see how it's left shifted. And now if we add the carry in, you can see how a bit is shifted into from the left over here. Now let's go to, this is where I'm checking the right shift again with hex 8 1. And you can see how if we shift this value over 1, we capture this 1 out into the carry out bit. And we can do the same thing when we left shift, and we capture this higher bit up here of the 8 into the carry out bit. I mean, it could be useful. You may never know when you need to grab that carry out bit. You may never care about it. You never know. Now we go to the next operation, which I believe is the not. So we're just taking the hex AA. If we not it, we end up with hex 55, right? We're just flipping each bit. So that's what you do with the not. Now we're ANDing them. So here's the value of B right here, right? It's 55 and A is AA. So 1010 and 0101, we end them all together. We get 0, and we get our 0 flag, which is good because it should. Now if we take those same values and we OR them together, we end up with all ones, no flags. Same thing with exclusive OR, we end up with all ones, no flags. And now here's where we're going to do our two compares. So this one is, we're changing the value of B to be equal to A. They're both hex AA. And when you exclusive OR that, you get 0. And then we also get our 0 flag and our equal signal comes on, which is good because A is equal to B, and that's what we want to happen. And now I'm going to change, right here is where we change A to hex AC, make it a little bit bigger than B, and you can see our A larger signal lights up with the comparator. And we have verified the ALU component. We've gone over 2 components of the microprocessor so far. Hang in there, we're going to get to some really good stuff in a while, especially when we get to the control unit. There's going to be a whole lot of Verilog going on. Thanks for watching this video, and I hope to see you on the next one, and also have an awesome day.